Okay, so this is the the work that was done by my PhD student Prem Kumar and a former postdoc Atulya, and also based on some ongoing work with our MSc student Ritik Theory and PhD student Prem Kumar on higher order TCL divergence. Okay, good. So what I'll do, so let me give you the brief outline. I'll talk about briefly about this Gorini-Kosakowski-Sudarshan-Lindblad master equation is microscopic approach, and then I'll talk about this perturbative approach to talk about this time convolutionless master equation, and then I'll consider the spin boson model to talk about this time convolutionless master equation and their higher order forms, a bit of applications thereof on this double quantum dot system, and the benchmarking. So whatever we have done, how good or bad it is in terms of some existing solution, that I'll talk about. And then finally I'll talk about the divergence of this time convolutionless master equation if you go to higher orders, and then summarize. Okay, so let's talk about this microscopic approach to Gorini-Kosakowski-Sudarshan-Lindblad master equation. Maybe most of you know that this was done sometime during 70s independently by Gorini-Kosakowski-Sudarshan and Lindblad. Okay, so what I'll talk about today is weak system bath coupling. So we have my quantum system and it is interacting with this environment, which can be a thermal bath or something else, but the interaction is weak. When we talk about GKSL master equation, the interaction is really weak, we call something like ultra weak. Okay, so the total Hamiltonian of system bath is like HS, which is the system Hamiltonian, HB, which is the bath Hamiltonian, and HI, this is the interaction Hamiltonian. And now if I write down the Schrodinger equation for system plus bath together, which is considered to be a closed system, then the density matrix of system plus bath together is rho at time t, rho t, and I take the Schrodinger equation which is ddt of rho t as minus iota commutator of this HIT and rho t. So I have taken throughout this h cut equal to 1, and HIT is basically the the interaction picture form of the interaction Hamiltonian. So H naught is the total free Hamiltonian, that means HS plus HB, and so this is the interaction. So basically this equation 2 is the interaction picture form of the time evolution of the total density matrix of system plus bath. Right. So now if I now take, for example, if I integrate this, so this equation 2, what I'll get is rho at t is equal to rho at 0 minus iota this integral of this commutator HIS and rho s, where s runs from 0 to t. Okay, so this is the integral form of this Schrodinger equation 2. Now let's do something. So on the right hand side of equation 2, I put this integral form of rho t given in equation 3. So if I do that, I will get this equation 4. So you have the double commutator now on the right hand side. So your Schrodinger equation is the so now you take the trace over the bath degrees of freedom. So what you will get is the state rho s at time t, and you take the time derivative of that. So you will get this expression on the right hand side. Okay. So first one is the single commutator, and second one is the integral of the double commutator. Okay. So now what I can do is I can take this first term on the right hand side of equation 4 to be 0, and without loss of generality we can do that, because in order to do this thing I'll have to shift the energy origin. So this is the free Hamiltonian H naught, which is HS plus HB. So I can redefine it, this free Hamiltonian, by shifting the energy origin, so that I can take this trace of B over this commutator to be 0. This I can do without any loss of generality. Okay. So once I do that, then this equation 4.
Sorry,
yes.
Could you make, I mean, we do not see the content after, thus we have now, it is, yes, now it is visible. Yes,
okay, sorry. Yeah. So now if you look at this equation, so if you insert this assumption phi, which as I said we can do always, so then this equation 4 will become this time derivative of the system density matrix at time t, and this is the double commutator, integral of the double commutator with a negative sign. Okay, good. So now what you can do now is, so therefore you have this equation 6, which which is exact. I mean, no assumption. Of course, this equation 5, this assumption is there, but as I said, this is without loss of generality you can do. So this equation 6 is exact. So this is the time derivative of system density matrix, and that is what we want to see. So now you start with assumption. So this is called microscopic derivation of the GKSL master equation through this assumption. So what you do, you assume that the time evolved state of system plus bath, so I am talking about equation 7, is approximately equal to the time evolved state of system tensor product a fixed state of this bath rho b, and this is assumed for all t greater than equal to 0. So it means that the dynamics, so the interaction with the bath is so weak that it does not create any correlation between the system degree of freedom and bath degree of freedom. Okay, so this is your Born approximation. So once you use this Born approximation in the previous equation, equation 6, like this equation 6, then what you will get is basically you replace these rho a, I mean the time evolved state of the system plus bath at time s. This should be equal to the basically rho s at s tensor product rho b. So this is the equation, dynamical equation of system density matrix after Born approximation. Okay, good. So then what you do is, now you can go for Markov approximation. So before going to Markov approximation, this interaction Hamiltonian HI, I can always write as sum of tensor product of, this is the A alphas are system operators, observables basically, and B alphas are bath operators, observables. So given this form, this I can always take. I can then write down the interaction picture form of HIT. So this will be basically A alpha t and B alpha t. So A alpha t is the interaction picture form of A alpha with respect to the system's free Hamiltonian, and B alpha t is the interaction picture form of B alpha with respect to the bath's free Hamiltonian, Hs and Hb. Okay. So using this equation, I can rewrite this master equation which we talked about, this equation 8, after the Born approximation. I can write it in this form. So the time derivative of system density matrix is equal to, so this equal to means approximately, of course, based upon the approximation like Born approximation. So this is what you will get with this Hermitian conjugate. So this is the bath correlation function. So 2-time correlation function B alpha t and B alpha prime s, and this is taken with respect to the bath's initial state, and according to Born approximation, that initial state does not change because you assume that the bath degrees of freedom is huge compared to the system's degrees of freedom. So this equation 10 is what you get after using this this form of HIT and the Markov the Born approximation. Okay. So what we assume is that, and this is what it happens, is that the bath correlation time, so there is a time scale, bath correlation decay time scale, system relaxation time scale, all those time scales are there. So you assume that the bath correlation time scale is much faster. So the bath correlation decays at the time scale tau b, and system relaxes. So it will relax into its equilibrium state with respect to time scale tau r. So weak coupling means that this tau b, that means the bath correlation decay time scale is much smaller than the system relaxation time scale. Okay, and this is what we mean by Markov approximation, and this you can assume because you are assuming that the interaction strength is very weak, and as a result, in equation 10 we can replace this rho system's density matrix at time s by system density matrix at time t. Okay? Because for large time, that means time much greater than tau b, there is no change, because so basically what we assume is that there is no back action from the system, from the environment to the system because of system bath interaction. Okay. So although the bath correlation time, it changes very fast, it decays very fast, the system does not evolve at that pace. Okay. So we have now the Born approximation and Markov approximation, which will give rise to this equation 11. So this is the time evolution equation for the systems density matrix, and on the right hand side you have this quantity, and this equation is known as Bloch-Redfield master equation. Okay, master equation because it gives rise to the dynamical equation for system states density matrices. And as you can see on the right hand side of equation 11, that this is time local. So only t is involved here. I mean, when you talk about this rho s at t, only rho s t is involved. If you compare it with this equation 10, you see that rho s is involved. Okay. So the previous time is involved. Here it is the present time. So it is, therefore it is called time local, and this time local master equation is relatively easy to handle with. Otherwise, if you have the memory like this Nakajima-Zwanzig master equation, where you have all the previous memory, things will become much more complicated. Of course, this is true under certain assumption that I mentioned. Okay. So in fact, if you go to this equation 8 and replace this rho ss by rho st, you will get this equation. So equation 8, if we, it is not working here. So yeah.
Could
so
you also zoom out to 80% in Acrobat, because the bottom of the page is cut off?
Oh, okay. So
yes, this lens
this is fine.
minus. Could you once more? Could you press? Yes, this maybe once
this is
more.
Fine.
Yes.
Okay, maybe smaller. Yeah.
Yeah. Right. This is correct. Thanks.
Yeah. Okay. Good. Okay. So this is your equation 8, and here if you replace this rho ss by rho st, then you will get this Born Markov. I mean the Bloch-Redfield equation. So this is your Bloch-Redfield equation. You can also express in terms of this interaction picture, interaction Hamiltonian HIP. So anyway, so we can refer either equation 11 as Bloch-Redfield master equation or equation 8. Okay, good. So still this Bloch-Redfield equation, this of course is a master equation, but the problem with this is that this is not completely positive. So it does not give you the physical dynamics. Okay, although this is quite good at explaining dynamics, I mean giving results to weak coupling dynamics, but this is not completely positive. Okay, so now we'll do one more approximation. So we have made Born approximation, Markov approximation, and these two approximations will give rise to the Bloch-Redfield equation. Now we'll do one more approximation. So before that, I will represent, basically I'll use some kind of Fourier representation of the the interaction picture, interaction Hamiltonian, and instead of A alpha t, I go to its frequency domain, and where this A alpha t is basically it is punch between this energy, this is the system energy eigen operator corresponding to energy epsilon, so pi alpha and pi alpha prime, and where the energy difference epsilon prime minus epsilon is basically omega, because you remember we have taken h cut to be equal to 1. So this is actually the energy, right? So with this, now you can write down again the Bloch-Redfield equation in this form. I mean, these are the simple calculations. And now you see that here on the right hand side of equation 14, you have summation over alpha prime is there, of course, but also this frequency or energies, omega and omega prime, right? So if this omega minus omega prime, it is much greater than the inverse of the relaxation time, then you will have fast oscillation because of e to the power minus omega minus I iota omega minus omega prime into t, and therefore those oscillations will, as a whole, will get cancelled, except for the case where omega is equal to omega prime. So actually this is the assumption which is called rotating wave approximation, where you assume that these two frequencies they match, okay, because the bath has several degrees of freedom, so it will have several energy levels, but you identify only one of them. Okay, so if you do that, if you use the rotating wave approximation, basically what you will come up with this master equation, equation 5, so which is this time evolution of the system density matrix, which is the first part is the unitary part, which is the commutator with a modified Hamiltonian, which is called HLS, which we call as lamp shift Hamiltonian. So this is a modified version of the actual system Hamiltonian HS, plus a dissipative term d of rho st, and dissipative term has this particular form which we call as the GKSL form or Lindblad form, whatever you want to call. So this A, beta, omega, these are the system operators. So here you have first one is A, beta, omega, rho st, A alpha dagger omega, minus this is the anti-commutator of A alpha dagger omega, A beta omega, comma rho st. Okay, so these quantities, these S alpha beta, gamma alpha beta, all are given in terms of this Bath correlation function. So you look at the Fourier transform of this 2-point Bath correlation, B alpha dagger IS, B beta 0 with respect to this initial state of the bath, and then take the kind of Fourier transform, so which you call capital gamma alpha beta omega. So the real part of that is the small gamma alpha beta omega, and something like imaginary part you can say, I mean 2 times the real part of this is small gamma omega, and the imaginary part of capital gamma omega is this S alpha beta. So here of course we have assumed that this time t is much greater than the Bath correlation decay time scale, because Bath correlation decay time scale is very small, and as a result in the previous case you see that here in equation 18 the time integral is from 0 to infinity, whereas here in equation 14 it is 0 to t, and this, so therefore this integral 0 to t can be replaced by 0 to infinity, because the Bath correlation it decays much faster. Because this is the tau b is the Bath correlation time scale. So you can at ease easily replace this time integral 0 to t by 0 to infinity. Okay, good. So therefore you have this equation 15, which is called the GKSL master equation, which you have obtained by using these 3 assumptions through this microscopic derivation, Born approximation, Markov approximation, and rotating wave approximation. And one can prove that the equation 15 corresponds to a completely positive dynamics. Here the entropy of the system will always increase and it will reach the equilibrium state. Okay. So if the bath is thermal bath, it will reach the temperature of the bath. Okay. So that was about the GKSL master equation, where the interaction with the bath is very weak. Now let us talk about the perturbative approach. Okay. So what we assume is that the interaction Hamiltonian HI is a kind of perturbative. It's not very strong. It is weak. It's not ultra weak, but it is weak. So in that case, you can write down the Schrodinger equation of system plus bath together in this form: d rho dt is equal to minus iota. Then lambda is your perturbation factor. And this you can write as some Liouvillean operator curly LT, lambda curly LT acting on rho t. Okay. And rho st is of course its reduced density matrix. So now what you do, instead of taking the Born approximation, you consider a projection. So P is a projection operator, which when acts on the joint state of system and bath at time t, it will give rise to the state of the system at time t, tensor product the fixed state of the bath, the state of the initial state of the bath. Okay. So this is something like Born approximation, although not exactly. So this projection so basically this P and Q, it projects out the relevant part and the irrelevant part. So P and Q are orthogonal projections. Okay, like where Q of rho t is this. Right. So therefore P plus Q is equal to identity on system plus bath. P square is equal to P, and PQ are 0 because they are orthogonal. Similarly, Q square is equal to Q. They are also projectors. So therefore, if you now look at equation 21 and then project apply the projector P on both sides of this equation 21, you will get this equation 25. Here I have replaced the identity by P plus Q because that is my identity, and similarly you can apply this with Q also. So if I now solve, because I am interested in P of rho st, because that will give P of rho t, because that will give me this rho st, a trace over B of rho t. So I am interested in that. So what I need to do is I solve this equation 26 for Q acting on rho t, and then use it on the right hand side of equation 25 to get P acting on rho t. So yeah, so that can be done by using some kind of propagator. Okay, so you can look at this equation 26, and then you can try to solve it. So Q of rho t will be something like this. So Q at rho 0 plus lambda times this Carly GTS is the kind of propagator. So this is the the backward time evolved exponential. So this is your Liouvillean. Anyway, so now what you assume is, just like in the previous case, that your initial state of system plus bar is the initial state of your system, which can be anything, tensor product a fixed state of bath rho b. Okay, and you can show that for this case, therefore Q of rho 0 will be 0, and therefore GT this is 0. So anyway, so using this, you can now write down this Q of rho t, and therefore you can use that to figure out what is rho s. In fact, there will be another evolution, time evolution, basically backward evolution. So using all this, so this is your sigma t. So Q of t is basically this identity minus sigma t inverse, then sigma t P of rho t. So this is ultimately the, and here we have made no assumption till now. Okay, so this will give you basically the equation for P of rho t, where f of t is this operator lambda p l t etc. Okay, so using this definition etc., you can write down now this time derivative of rho st, which will be whatever is written on this equation 36. Okay, good. So now you introduce this perturbative approach. So you assume that this LT1, that means the Liouvillean at T1 times Liouvillean at T2 etc. times Liouvillean at T2n plus 1. So there is 2n plus 1 such time points, and you sandwich it between these two projectors on the left and right. You assume that this is 0. Now this is not not actually very bad assumption, because if you take your bath to be something like a Gaussian state etc., you can do that. It is not very difficult. So ultimately, what is the point of this assumption? Basically, what you can show is that, you see, this lambda is our perturbative factor. So you can expand this identity minus sigma t inverse as a power series in lambda, okay, because lambda is the perturbative factor, and that will give rise to this f of t, this operator f of t. Okay, so if you use perturbation, you will have all the powers, lambda, then lambda square, then lambda cube etc. But under this assumption, what you can show is that in that power series, only the even powers of lambda will survive, the odd powers will go away. So in this expression of f of t, you see that the first term is lambda to the power 0, then lambda square f2t, lambda to the power 4 f4t and so on, and f0t is 0. Basically this is identity, there is no interaction between the system and Hamiltonian. Okay. Right. So once you do that, then you can write down what will be your f2 of t, f4 of t. So these are the generators of higher order TCL. So f2t is the generator of the second order TCL, f4t is the generator of fourth order TCL and so on. Okay. So if you stick to f2 of t, then you will get this equation 40, which is the time evolution equation for rho s at t. Okay. And this is exactly the Bloch-Redfield equation. So you see that if you go to this time convolutionless master equation through this perturbative approach, then up to the second order in perturbation, what you get master equation is nothing but the Bloch-Redfield equation. Now, as I said, Bloch-Redfield equation is not a completely positive dynamics. in order to make it completely positive, one way out is to assume also the rotating wave approximation, but we are not assuming rotating wave approximation while dealing with TCL. So TCL2 is basically the Bloch rate field equation. Okay, good. Now, you can, so you see that if you use all this approximation, etc., and this operator form, what you will get is this equation finally. So d rho s dt is equal to lambda square f2 of t plus order of lambda to the power 4. So therefore, this equation is correct up to basically the third order in lambda. Anyway, third order will not appear. So this is what you will get for TCL2. So this is your TCL2 master equation, time convolutionless order 2 master equation. Okay. So now the question is, because this is a perturbative approach, how accurately it will approximate the actual dynamics, okay? Because actual dynamics has to be a completely positive, but this is under this perturbative approach. So one can show that the dynamics, that means time evolution of the system, for TCL2 it is accurate up to lambda square order, and TCL4 it is accurate up to lambda to the power 4th order. On the other hand, if you look at the steady state coherence, so the system will approach the steady state in general, and if you look at the coherence in the steady state, that means the off diagonal terms, that will be correct up to lambda square order for TCL2 and lambda to the power 4th order in TCL4. On the other hand, if you look at the steady state population of the system density matrix, then it will be correct up to 0th order in lambda and 2nd order in lambda square for TCL4. Okay. So this is, and this is something that you should keep it in mind. So for example, a TCL2n master equation retains the dynamics and the steady state coherences correct up to lambda to the power 2n. But the steady state population is correct only up to 2 orders less, so lambda to the power 2n minus 2. And this happens because, if you want to go to the steady state, you will have to go to the asymptotic limit in time, and that long time behavior will accumulate error. Okay. So that is why the populations are not correct up to lambda to the power 2n, it is correct up to lambda to the power 2n minus 2. Okay. So what is the idea? Idea is that you start with ultra weak coupling case, which will give rise to this optical master equation, this the GKSL master equation, and slowly you increase the coupling strain. So you go to the weak coupling regime, you will have this TCL master equation like Bloch rate field for TCL2, then TCL4, then TCL6, etc. So eventually our idea is that maybe it can also capture the intermediate level coupling, and maybe in some case the strong coupling cases also. So we will discuss about that. We will see that there are cases where this TCL higher order can give divergent dynamics. So therefore, this way of achieving intermediate coupling or strong coupling through this higher order TCL is not a good idea. Okay, but when the coupling is weak, this works quite well. Okay, and that also we will see. Okay, so now F4 of t, this is the 4th order TCL generator. It has all this integral form you can see, and so equation 48 will give you these integrals. So there are the 3 time integrals, and whatever they are inside this bracket, they will also involve frequency integral. Okay. So so I don't want to scare you with all these expressions. These are a bit scary, this F4 of t acting on rho st. So anyway, so this will give you the TCL master equation, TCL4 master equation, higher order TCL. So rho s of ddt of rho st, it is basically lambda square f2t acting on rho st, lambda to the power 4 f4 t acting on rho st plus order of lambda to the power 6. Okay. So this you can say that this is a much better approximation compared to TCL2 or Bloch rate field equation to the actual dynamics. Okay, so now let us talk about a specific model when we discuss this TCL2, TCL4, etc. And the model is the spin boson model. So you have this single spin which is interacting with harmonic oscillator baths, okay, at different frequencies. Right? So these are the harmonic oscillator baths which acts on. So this is your HS. This is the free Hamiltonian of system, spin half system, and HB is the free Hamiltonian of the all the baths together. So baths are not interacting among themselves, and the interaction Hamiltonian, to make our life easier, you remember we have taken the interaction Hamiltonian to be sum over alpha A alpha tensor product B alpha, but you can start with the simplest case where you have only two terms. So lambda is of course the perturbation factor, perturbative factor, A tensor product B. So A is the system operator and B is bath operator. So I take this without loss of generality, I can take A to be of this form, arbitrary system operator. You can say that where is the sigma 2 term, but anyway you can choose a reference frame where you will have only these two terms, sigma 3 and sigma 1, and B is basically the position dependent bath operator. Okay, so this is something like Caldera-Leggett model kind of thing, okay, for this spin boson system. Okay, so now whenever we talk about the the infinitely large bath, it will have lots of degrees of freedom, and it will have therefore the frequency also continuum of frequency, the energy you can say. And in order to look at the properties of the bath correlation function, what is important is this spectral density J of omega. So you can take J of omega in this quite general form, sum over n Cn then Mn omega n. So Mn's are the masses of the individual oscillators and Cn's are the coupling factors, or you can say these are the constants, and then you will have these quantities eta t, nu t. So eta t is the imaginary part of the bath correlation function and nu t is the real part of bath correlation function, and this f omega is j omega times cot hyperbolic beta. So beta is the inverse temperature of the bath. Okay. So this j omega, the spectral density, is basically specifies the relative strength with which the system couples with the bath mode with frequency omega. So that is how it works. So in particular, if you can take j omega to be proportional to omega to the power s at low frequency. So omega is small, and there are three cases that you can consider for this particular form of j omega. Sub-ohmic case where s lies between 0 and 1, ohmic case s is equal to 1, and super ohmic case s is greater than 1. Okay, so we will consider this kind of spectral density now. So j omega is proportional to omega s. Okay, so using that kind of spectral density, you can now figure out this f4 of t, which is the generator of TCL4, and try to figure out the matrix element of it, and then t going to infinity limit. So the steady state behavior, you see that you have 3 time integral on the right hand side, and then the quantity within the bracket, this nu t, eta t, they involve frequency integral, as you see, eta and nu. So basically you will have 2 frequency integral and 3 time integral in order to figure out the matrix element of the TCL4 generator. Okay, right. So yeah, so here the problem is that because these are infinite integrals 0 to t, but the frequency integrals are from 0 to infinity. Okay, so we cannot just interchange the integrals, order of integrals. It may be a problematic thing. So it depends in which order you are doing the integral. So we have used this Mathematica to figure out the values of this integral. So I will not go into all these details. Those are there in our papers. Basically the integrals will be convergent if it satisfies this kind of condition, which is well known. And yeah, so therefore you can study these integrals and figure out when it will be convergent and not. So this is related to the basically the order of integration. So you all know that it will matter. So for example, if you interchange this order, this omega 2 omega 1 and omega 1 omega 2, you take the difference, this will be a non-zero number. So therefore it matters how will you do the integral. Anyway, so this we all know. So therefore, these so what I wanted to say is that these fourth TCl4 generator or even higher order generators are quite non-trivial to figure out, even for the spin boson model, and yeah, because it involves infinite integrals. Okay, right. So yeah, so in our paper we have given the methods how to do that, and I think there is also this GitHub code which is available for these integrals. Okay, so now the question is, you have this TCl2, TCl4, etc. For GKSL master equation, we know that the steady state is the thermal state. I mean, if you take the thermal bath to begin with, it will be the thermal state corresponding to the temperature of the bath and the system Hamiltonian. And that is for ultra weak coupling. But if you take now weak coupling, not necessarily ultra weak coupling, when you talk about this TCl and higher order TCl, then what will be the steady state? Okay. So what we have shown in our work is that in the case of TCl2, TCl4, etc., these master equations, you can show that the steady state is not exactly the Gibbs state, that means the thermal state, but it is a more general form which is called mean force Gibbs state. So what is mean force Gibbs state? Let's take the Hamiltonian of the SB. So SB is the total Hamiltonian, okay, system plus bath plus the interaction Hamiltonian lambda hi. You trace, so you take the e to the power minus beta HSB. So beta is the inverse temperature of the bath, and you take this trace over B and then divide it by the norm, which is the partition function basically. Z is equal to the partition function. So what happens is that if this lambda is small but not negligible, then this mean force Gibbs state is not equal to the Gibbs state. Okay, so Gibbs state is proportional to e to the power minus beta Hs. So you can show that this is generally not equal to the Gibbs state. So the system steady state will not be the thermal state. Okay, in general, whenever you have interaction strength which is not quite negligible, it is weak but not negligible. Okay, so our result says that the steady state for the higher order TCl, second and fourth order, that the steady state, system steady state equal to the mean force Gibbs state of the system. Okay, so this is what we have shown. I am not going into the derivation. So okay, so now about the applications of TCl. So you can show that the double quantum dot system, which is a semiconductor double quantum dot, where you have a charge qubit and the phononic bath. So this phononic bath acts at your bath and charge qubit acts as your qubit, and this together will form this spin boson model. So this is the the setup for this quantum dot. Okay, so this double, so you have basically two dots together, and then you can so therefore the question is that if we now study the dynamics of this charge qubit when it is in this double quantum dot scenario, then how will it behave? Okay, so in particular, if you take the spin boson model of this double quantum dot, you remember we had this Hamiltonian for the spin boson model. Let me go at it once again. Yeah, so this is the system Hamiltonian with this omega frequency. This is the bath Hamiltonian. This is the parameter for the perturbation, and then in A3 sigma 3 minus A1 sigma 1. So so for this double quantum dot model, you can take these parameters, like A1 is, so Tc is some critical time, 2 Tc by omega, A3 is epsilon by omega, epsilon is again some kind of energy, so this is a detuning basically, left right detuning, and this omega, capital omega, is this double quantum dot level splitting, and Tc is the inter dot tunneling time. Okay, so Tc is this tunneling time, and you take this phonon spectral density. Okay, J omega is this form, and this small omega, omega c, omega max, those are all phononic parameters. Okay, so this is the these are the parameters that you take for this double quantum dot when you treat it as a spin boson model. So when there is no interaction, then you plot the average value of sigma 1 at at time t. Sigma 1 is the sigma x, and you see that this is 0 because nothing is changing there. Okay, and sigma 2 average value is 0 because you start with the like a state along the z direction, and this is what the average value we will have. So all of these are constant because there is nothing acting on the, no interaction is there, only the sigma z Hamiltonian is acting on it. Okay, good. So now you go to TCl2 where these phonons enters into the picture. So because you have the phononic bath, and there so here also you have to take this lambda to be a small value, the interaction strength. So now you take a phononic bath. So this red curve is for TCl2 for sigma 1 t. So that means sigma x average value at different times. So you see that there is oscillatory behavior, but finally it reaches some equilibrium value. Similarly for sigma 2, that is sigma y, and for sigma 3 again it reaches some equilibrium value, and this dotted line is for the Gibbs state. Okay, so where this is ultra weak. So this is for TCl2. Now if you look for TCl4, so this is the green one is for TCl4. So you have a bit more oscillation in sigma x of t. TCl2 is the red one, and TCl0 is this straight line. So you see that the green one is a little bit more oscillating, and here also it is is approaching some equilibrium value, but higher than those for TCl2. Okay, so the question is which one is more correct. So this for this study, what we need to do is to, so as I said, these TCl dynamics, TCl2, TCl4, etc., they are not completely positive, but they are they have a memory. Okay, although it is time local, but they have memory, and so therefore they are approximately equal to some non-Markovian dynamics. So so in order to understand this non-Markovianity, this is a cartoon figure. So what happens is that under these dynamics, you start with two different orientation, so different configurations of these teacups. Here you have the tea and here you don't have. So ultimately what will happen after they approach the steady state, they will become the same kind. Okay, there is no difference. Okay? So basically under these dynamics, your distinguishability generally it loses, and this is so this is again a cartoon picture. So like if you take a coffee and you allow it to thermalize, so the temperature of the coffee will slowly go down and reaches the room temperature. So this is a kind of memoryless or Markovian dynamics. On the other hand, if you take a non-Markovian dynamics, this will also decay, go to the room temperature, but with some oscillatory behavior. Okay, so this is a thermalization with memory. Okay. So now, so how to understand these non-Markovian features? So there are different ways of calculating non-Markovianity. So the one which we are using this BLP measure. So you take the difference of two initial state or time evolved state and take the trace distance and multiply by half. This will give you some kind of distance, and then you evolve these states under your dynamical map. Okay, and then again take the distance and take the time derivative. So under Markovian dynamics, the distance will gradually decrease, so the time derivative will be negative always. But for non-Markovian dynamics, it can increase, decrease, increase, decrease, etc., and that will give rise to these revivals, okay, of the distance. Okay. So the revival, that means the non-Markovian feature, means that the sigma t, the distance should be positive at some point. Okay. So there is an information black flow. So this is your plot for TCl2 and TCl4. So for different values of the coupling parameter, so this lambda, capital lambda, comes from this bath spectral density, and T is the temperature. Okay. So we have plotted for TCl2 and TCl4 with the same capital lambda and T value. Similarly, TCl2, TCl4. So you see that the trace distance. So this TCl2 is a solid curve and TCl4 are the dotted curves. So you can see that these, for example, this green one TCl4 and dotted green is TCl2. So you see that the trace distance it is oscillating, but actually gradually it is going to somewhere else. Okay. So this wiggly behavior, which tells you that there is some kind of information backflow, okay, and that is happening because of the non-Markovian dynamics. Okay. So the trace distance decreases, but it decreases in oscillatory behavior. Okay. Right. So and then if you want to look at the memory effect, because TCl2, TCl4 all are non-Markovian kind of dynamics, although not completely positive. So, for example, on this left side top panel, you look at this this distance, like this the measure of non-Markovianity for TCl2. Okay, so you see that the distance as you go from bottom to top, it increases, and this is temperature versus this capital gamma, and so in this white region you see the distance is the highest, so distance is the smallest one. Okay. Right, and on this figure again, it is the measure of the TCl4 measure of memory. So you see that the TCl2 is a kind of overestimates, like if you look at this figure bottom left hand side, we have taken this non-Markovianity measure n TCl4 minus n TCl2. So you see that in the deep blue region this is negative, so that means TCl2 is more non-Markovian than TCl4. On the other hand, in this red region this is positive, so therefore TCl4 is more non-Markovian than TCl2. So basically in some regions of the parameter space, TCl2 is overshoots the TCl4 dynamics, and some region it undershoots it. Okay, right. And now if you look at how strong the perturbation is, you can take the ratio of this norm of this fourth order TCl and second order TCl. You see that the ratio will increase here on the black region, and near this, so this black line kind of thing, almost straight line, this corresponds to the Markovian case. Okay. So basically what we want to say is that TCl4 approximate the actual dynamics in a much better way from the dynamical point of view, from Markovianity, non-Markovianity point of view, it approximates it in a better way. Okay. Now the question is that we have done this higher order TCl, how good it is in terms of the actual dynamics. Okay, so we cannot do for arbitrary actual dynamics, we also cannot do for arbitrary spectral density. So what we have taken is the ohmic spectral density, because it is proportional to omega. So this is your which is known as the Lorentz root cutoff. This is the ohmic spectral density. Capital lambda is the Barth cutoff frequency. So basically you see that if omega is greater than or equal to this cutoff frequency, then this will basically go to 0, this GAD of omega. Okay. So for this choice of this spectral density, you can calculate the TCl4 dynamics coefficient and in the time domain, and basically you will have some infinite series containing something called Matsubara terms, and which has a thermal pole mu n s 2 pi n by beta, and basically the exact results, this contains infinite single and double sums over these Matsubara frequencies, and you can truncate these sums and it will provide an independent check of the general TCl4 result that we have done. So this is the comparison. So convergence of the Drude benchmark. Okay. So you look at the relative difference between the TCl4 result and this exact result with this Drude cutoff. You see that as you increase the Matsubara term, because you will have to anyway cut down the series, infinite series, as you increase the Matsubara term, the relative difference decreases. Okay, it goes to almost 10 to the power minus 7 order. Right. Okay, good. Now, so this is for the Drude cutoff. Now, there is also an exact numerical method for solving open system dynamics, be it Markovian, non-Markovian, etc. So, which is called hierarchical equation of motion, HEOM, right? And but the problem is this is computationally quite expensive, unlike TCl dynamics. Okay, right. So what we have done is we have calculated these TCl2 and TCl4 dynamics and looked at the fidelity under this TCl2 or TCl4 versus this HEOM, so rho H of T, and then 1 minus this fidelity. So fidelity 1 means this 1 minus fidelity should be 0. So if you plot it, the dotted blue one is for TCl2, so the error is bit higher compared to the TCl4. So if you take TCl6, it will be even lower. Okay, so it tells you that, and these are all like 10 to the power minus 6, 10 to the power minus 7 of the order. So it is quite well matching with the exact dynamics. Exact means, of course, under this HEOM. Okay. So finally, so I'll just talk about, I'll take another 5 minutes or so. So I'll just talk about these. So I said that, you know, the idea is you go in higher and higher powers of TCl. Of course, you will have to deal with these higher order integrals, that is fine. But whether it can give rise to, you know, some dynamics which is you know, at the intermediate coupling level, okay, or strong coupling level, right? So it turns out that no, unfortunately, we cannot do that for every kind of spectral density, every bath temperature. We cannot do that. Okay. So for example, this Lampard et al. They studied this TCl dynamics, higher order TCl dynamics for the spectral density of this form. Okay. So J omega is of this form. So this is something like this what we have originally used, J omega proportional to omega to the power s, something like that. And this capital theta omega is the Heaviside step function. So at 0 temperature, so you take the bath at 0 temperature, if you calculate the bath's correlation function, it behaves like a polynomially, t to the power minus s minus t, okay, right? And generally for other kind of baths, right, okay, so this is, or if you take the bath temperature not to be 0, then the decay will be generally exponential, the bath correlation you know, decay. But here it is a polynomial decay. So this is a specific case, and but if you take the non-zero Bohr frequency omega, then the leading, you know, long time contribution from TCl2n, this will be of this form. Okay, again at 0 temperature bath. So this is t to the power n minus s minus 2. So therefore, if I take n to be greater than s plus 2, you see that TCl2n generator, this diverges, okay, because this is for long time limit. Okay, so this is diverges polynomially. So basically these, what is the root cause of this divergence? Okay, so this is what we are trying to figure out. So recently there is some work by Dragomir Davidovich, who suggests that this divergence, what I said for this particular spectral density and at 0 temperature bath, this is caused by, you know, vanishing singular values of the corresponding dynamical map. So dynamical map is a kind of CPTP map, actual dynamical map at finite time. See, the singular values of the dynamical map, eventually it will it will vanish.
Sir?
Yeah.
Excuse me, sir. Sir, you
Yes.
have 10 minutes left, sir. Actually,
okay.
In 5 minutes you can complete, and in 5 minutes you can discuss.
Sure. Okay.
Thank you, sir.
So this, you know, ultimately, if you look at GKSL or other master equation, wherever it attains this the steady state or equilibrium, and this the dynamical map singular values, they will eventually vanish. So at large time limit. But what is happening here for this kind of spectral density or 0 temperature bath is that some of the singular values, they are vanishing at a finite time. Okay, and this happens because you have a competition between the exponential decay for large time limit and polynomial decay at finite time regime. Okay, so there is a kind of destructive interference between these two kinds of decay. We'll see in figures also, and that is basically the root cause for this divergence. And although the actual dynamics is not divergent, but TCl generators will become divergent. Okay, right? So so basically, you know, you take this rho of t, and this capital lambda t is the dynamical map corresponding to the evolution, so which acts on rho of 0. So the time derivative of rho of t is basically L of t, the Lenglardian acting on rho at t. So L of t is lambda dot t times lambda inverse t. So therefore, if you have divergent, so that means if the singular values of lambda t somehow vanishes, for finite time, then of course L of t will become divergent. Okay. So in fact, if you take a single qubit system whose block vector component can be written in this form under this map, okay, then and you can look at the singular values. Basically, these singular values will, the sigma 3 and sigma 4 will give rise to the coherence of the density matrix, kind of. So we have used this tempo simulation data, and this is quite it is resourceful. And if you plot the logarithm of sigma 4, magnitude of sigma 4, which is the singular value, you see that at finite time of like time equal to 50, you have this the log of sigma 4 magnitude is very, very small, so almost 0. Of course, a long time limit, so this part on the right hand side, it is exponential decay, but here on the left hand side, this is kind of polynomial decay, and this is for the sub-ohmic case. So S is less than 1, and lambda square is the interaction strain, which is also small. So for the sub-ohmic case, for the ohmic super ohmic case, so S is greater than 1, so S is 1.25. You see that again you have the kind of oscillatory behavior. It is going towards 0, this logarithm of magnitude of sigma 4, and ultimately it will exponentially decay. Same is the case with ohmic but S is equal to 1, and you see that initially they have this algebraic decay, and then finally it will decay exponentially. Okay, and I have taken another sub-ohmic case for sigma 4, and you see that this is also decaying exponentially. So you see that so the singular value, the smallest singular value, you can say, it is going towards 0 even at finite time. Okay? And you have this competition between algebraic decay and exponential decay, right? And that will give rise to the divergence of the TCL, higher order TCL. And so therefore the question is how to avoid this divergence in order to get a better approximation of the actual dynamics. Okay, so let me conclude. So what we discussed is this Born, Markov and rotating wave approximation, which will give rise to this time local optical master equation or GKSL master equation. Then we discussed about the projection operator method that gives rise to this exact time local TCL equation, and by expanding the interaction in terms of lambda, the coupling strain. TCL2 is basically the block Redfield equation. TCL4 captures the next correction to the dynamics, steady state coherence and steady state population also. And general TCL4 expression can have positive or negative effects on the memory of the system. As I said, sometimes it can overshoot the non-Markov unity or undershoot it. Okay, and you can of course see that comparing with HEOM, the hierarchical equation of motion, you can see that TCL4 works better compared to TCL2. And long time TCL, higher order TCL, basically from order 6 or onwards, when you take 0 temperature bath and sub-ohmic case, it can give rise to the divergent generator, and because there is some kind of competition between exponential decay in infinite time limit and polynomial decay or algebraic decay in the finite time regime. Okay, and the map, dynamical map under this TCL will become non-invertible. Okay, so yeah, this last part we are still working on to understand why it is diverging, how to avoid that, etc. Okay, so yeah, thank you for your attention.
Thank you for a very nice talk. I have, and it is very interesting and informative. So allow me to ask 2 quick questions.
Yes.
So
yes, please go ahead.
Thank you. So you have discussed JKSL approach. So
GKSL
my question
master equation. Yes.
Yes. What about stochastic differential equations approach? Will we see the same or similar effects or results and see also divergence in dynamics as in the case of TCL? Could you comment?
Not be. Okay, may not be. Yeah, because the stochastic master equation which you are talking about, this Langevin equation, right? Kind of.
Yes.
So quantum Langevin equation kind of thing. So yeah, so the stochastic master equation, yeah, I am not sure whether you get to see, but the problem is that if you increase the coupling strength, okay, then I'm not sure how good the stochastic master equation will be, because people have been struggling with the strong coupling case, okay, even the intermediate coupling case. So I'm not sure whether you will get to see the divergence, but what you may get is not giving the results which are kind of matching with the system dynamics. Okay. So that may be an issue. So divergence may or may not arise. I am not very sure about that.
Mhm. My second quick question. If quantum effects, I mean, if you're considering second order or fourth order this terms in your expansion, so
Yes.
you may not see the quantum effects when maybe they will occur at longer interaction times. So in that case, what approach do you propose? A numerical approach or maybe something else?
Okay. So these TCL, through this TCL, of course TCL is valid only for weak interaction. Okay. So I cannot take it to interaction state more than weak. I'm not generally it will not be valid. But the quantum, I am not sure what are you referring to by quantum effects. Are you referring to some kind of coherence or so
Allow me to refine my
yes,
question.
yes.
Quantum effects, I mean Wigner negativity, for example.
Okay.
So this could be entanglement, for example. So effects like that.
Okay. So yes, so the long time limit, of course, you may not have quantum effects, because the system will eventually go to a steady state, which may be the equilibrium state. Okay. So there you will not have any coherence. You may not have any even kind of correlation with the bar degrees of freedom, etc. But so with this projection operator method, which we considered in TCL, already you have destroyed the correlation, if there is any, between system and bath. So that has already destroyed it. Okay. But yes, coherence part of the system itself, it will be there to some extent, because if you look at the these plots that I mentioned earlier, yeah, so these are they are decaying algebraically at a finite time, but before that there is some coherence, because as I said, the sigma 3, sigma 4, they are related to coherence of the system. So it will have some coherence, and after that also there will be some coherence, maybe not that as good as on the left hand side of this time. So it will be there to some extent. So if you consider coherence, system coherence, as a signature of quantum behavior, yeah, it is there, it is captured.
Hello, sir. I have a question.
Yes.
So, for the divergence, for the higher orders like TCL2 and TCL4,
Yes.
did you do the entropic approach? How could you do the using relative entropical divergence for this divergence?
We have done some entropy calculation there. There also you see similar kind of thing, like, because it is non-Markovian in nature. Again, I should emphasize that this is not a physical dynamics, this higher, TCL2, TCL4, etc. But they have a kind of non-Markovian characteristic. Okay. So because they are not completely positive. Yeah. So we have I have not given the plots here. We have done some calculation of the entropy, like this phenomenon entropy of the system under the dynamics, and it gives like some kind of oscillatory behavior here also. Okay. And particularly
higher orders also,
higher orders also, yes.
Thank you.
Hello, Sibasish. This is
Yes.
Usha. So I will just ask you some, take advantage of this. It was a very interesting talk. So I just wanted to know, where you mentioned about two different kinds of stationary states. That is, it's not a thermal state is what you mentioned. So I was wondering, suppose I had taken a 2-qubit state, and then allowed it to reach whatever is a stationary state, would there be any specific features like entanglement still survive in the TCL2 and TCL4 kind of situations? This is just curiosity.
Okay, so I mean, it depends. So the question is that most of these dynamics, particularly when you take this weak coupling or ultra weak coupling case, the system will have a steady state. Okay, right? Now, question is, the steady state, does it correspond to this quote unquote thermal state of the system, or does it correspond to something else?
Correct.
So what we try to show is that CL4, etc., where the coupling is weak, the steady state is not actually thermal state, but a generalized version of that, which is this mean force give state. Now, if you go to higher order TCL, or if you increase the coupling strength, this part I don't think we can say at this point of time, that whether the steady state will be something more general than mean force give state or something like that, that we cannot say. And as a result, it is well, so whether the entanglement will be there, will be between the system and the bath, maybe it will not be there, but
not entanglement.
Yes. Hello.
Not an entanglement between bath and system, but if a system itself is a 2-qubit system.
Right. Okay. That's I understand. Yeah, so there it may be there. I cannot say at this point of time. Okay.
So also it is something, it reminds me of what are passive states, and if I take multiple copies, it will reach thermodynamic limit, where you do end up with a thermal state. But these are difficult questions, I know, but just I wanted to say, steady states maybe.
Yes. We are looking at different kind of baths, like one easy thing is to take the standard thermodynamic bath, just some temperature bath. More general thing is that you take your bath to be many body system, where you assume that ETH holds good there. Okay? So that locally this is thermal. So what happens there?
Excuse me, sir.
Yes. Thank you.